let me start the recording. So welcome back, everybody. Happy Garbage Day. This is one of my things because as someone who's at home a lot, the only way I can keep which day it is straight is to use Garbage Day as my anchor. Because I know that if it's Garbage Day, I say, I'll see you on Thursday. And if it's not Garbage Day, I say, have a good weekend. So happy Garbage Day to everyone, which means Tuesday, where I come from. I have not downloaded Homework 0 yet, but if you haven't done so, there's no points for being late. Just please go ahead and finish it. That way you can get your 2 points extra credit and demonstrate that you know how to use the system. I also had some scheduling announcements for next week. On Thursday of next week, on the 8th of September, we are getting kicked out of this room to have comprehensive exams, so we will be meeting only on Zoom instead. So I will be coming to you from my basement without a mask on for a change. That will be such a treat. And I also have note here, office hours next week only are moving to Tuesday, Thursday after class. Monday is a holiday, Labor Day, so we won't have any classes, and so I'm not having office hours that day. And on Wednesday, I have an appointment that I could not reschedule, so we're doing office hours after class on Tuesdays and Thursdays, just next week. So any questions on that? No? Okay, and Tuesday's stuff is ready. We'll see if we need to get new stuff up for next Thursday or not, but I will always let you know as soon as I post something new for you to download for class time. I had a question over email about example papers using longitudinal analysis. Some folks are interested in getting a sense of how these models are used or how they would be talked about. And for that, I can point you to my webpage. So on my webpage, lisahoffman.com, of course, I have research publications as one of the tabs on the top, and I have different areas of things that I've contributed to. And I have the most stuff up for what I'm calling multi-level models, how to in practice. And so the first section, all of these articles are things that I've written that I would consider tutorials or explanatory pieces on how to do this stuff. Then there's various examples of papers that I've helped write where the focus is modeling within-person change, so growth curve type analyses, as well as modeling within-person fluctuation, so like intensive designs. And then multi-level models for more unique applications in terms of repeated measures, experimental designs, cross designs, and then a few at the bottom even about genetics. So I can show you how to estimate heritability, for instance, out of a multi-level model if that's something that you want to know how to do. So I just wanted to point out, and yes, all of the papers are linked from here, and I haven't gotten in trouble yet for doing it, so I'll continue to do so until someone yells at me. But I've got other stuff up here, but for this class, this is probably the most reasonable or useful thing. So, and of course, if you haven't seen it yet, the Piles of Variance website for the book has every single model that's in the book in 4 different programs. It also has, at the top of this website, a comprehensive sort of syntax guide that I made out of the official documentation for how I'm using all of the commands. That way they're not annotated on this site, but they're annotated in class. So just wanted to point out those resources to you if you are so inclined. So any questions about that, scheduling or otherwise, before we start? All right, then I will shut that down. Make sure that I'm recording, of course, very good. And the microphone appears to be working, so let's hope that that continues to be the case. We've got some new stuff to talk about today, transitioning from the world of cross-sectional analyses into the world of longitudinal analyses. Are we ready for this? All right. That's an enthusiastic set of head nods. Thank you very much. All right, there we go. So I will start there then. So, orienting us back to where we have been as a baseline for where we're going. So everything we're going to do in longitudinal starts with a baseline of a general linear model. And by that, I mean this type of setup, where it would look something like this. In a general linear model, it is designed for data in which each person has one outcome. So a univariate type of analysis where there's independent sampling. So we have y sub I in this notation because each person gets only one y, is a function of the part in red here. And the idea of this part in red we introduced last time, model for the means. So that's the part that pertains to how the predictors relate to an outcome. So we would have different types of predictors potentially in here. So for instance, if x1 and x2 were quantitative predictors, then I might call this a multiple regression model or a linear regression model. multiple linear regression, if you want to sound fancy. If x1 and x2 were dummy codes that indicated group membership, then what would I call this instead? What do you think? If x1 and x2 were dummy codes that indicated group membership, then I'd use a different name for the same model. ANOVA, yes, analysis of variance. And if I had a mix of predictors that were quantitative and categorical, I might call that ANCOVA, or just regression, depending on who you talk to. So from this point forward, there are no special names for different kinds of predictors. Just don't worry about that part. The special names have to do with the other side of the model for the variance. So this E thing. Each person only has one E residual because they only have one Y. And E describes how far off the actual outcome is from the one that's predicted by the model fixed effects, and they multiply the predictors. So in this case, E is sufficient if we only have one outcome per person. We need some more stuff, though, if we have more than one outcome per person. Question already?
Yeah, so is the model for means a structural model, and then model for variance is the measurement model, or is that different?
No, I would not use those terms.
Okay.
You could say structural for the model for the means, but I would say either error or stochastic.
Okay.
The model for the variance is all about the residuals, the part that's left over, and whether there are relationships in those leftover components across outcomes because of the sampling design.
Okay.
Yep. That's where terminology, I think, does not help. I would not use the word measurement model for this.
Okay.
I think it could cause more confusion than it would help. So I'm just not going to use that term. In general linear models specifically, the reason that I can talk about regression and ANOVA and ANCOVA all as one thing is because all of them share this common system of what we refer to about E. In those models, E is supposed to be independent, it's supposed to have constant variance across all the predictors and all the people, and it's supposed to be normal. So I can switch out this type of E, for instance, if Y were a binary outcome, then I wouldn't have an E here because we'd say that the binary outcome has a fixed variance that goes with the mean, or other kinds of things for designs in which we're still talking about cross-sectional variation only. But in our class, we're sticking with conditionally normal to begin with this semester, and then adding stuff to the model that takes into account the fact that we have longitudinal data. So just to remind you, some words that you're going to hear a lot and to make sure that we are all on the same page with what they mean. So we will talk about means, variances, and covariances quite a bit. So this is just to remind you that you've seen this before, in fact. So variance is the idea of how far off you are from something. What that something is dictates then what kind of variance it's talking about. Covariance we will talk about a lot, and that's one of those things that sort of gets stepped over on the way to correlation. But covariance is a very prominent term in this class as well as in the SEM class. The idea of covariance is whether two outcomes go together, and it's in the scale of the original variables. So we would multiply the deviation for one variable relative to the predicted value by the deviation from another variable relative to its predicted value, and then divide that by n. That's covariance. And then we can take that covariance and standardize it into a correlation that runs between -1 and 1, which is a lot easier to interpret, but it loses the information about the scale. So one of the things that we have to make sure works in terms of the models that we fit is that it can adequately reproduce the patterns of covariance across time, not just correlation. Correlation is the relationship. Covariance also includes the scale in terms of the variance as part of it. So covariance is scaled, correlation is scale-free. Can I share screen, please? Why, yes, wouldn't that be a great idea? Thank you for saying something. Is that better? Participants can now see your screen. Yeah, I thought I was forgetting something, and I was. I just didn't know what it was, so thank you. All right. So you've all seen this before. I just wanted to remind you of these things. So let's start with some pictures and some notation then. So if I know nothing else about a person, what's my best guess for what their outcome's going to be? The mean, right? Because that's a reasonable thing to start from. So for instance, if I had this model right here, which those of you who went through 6242 or 6243 with me will recognize as an empty model. More specifically, it's an empty means model because we're talking about the fixed effects in particular. And the term empty means no predictors. Now, I use an empty model in those classes as a pedagogical tool to come up with the idea of what is the most variance that an outcome can have, and then how do we track what happens to it as we add predictors. In this class, everybody starts with an empty model. It's not just a pedagogical tool, it is something you would report in a manuscript. Because what we're going to do with it is figure out how much variability we have, not just in terms of the number, but of each kind. How much of the variability is because of the cross-sectional variation that we started with, and how much of it is because of the longitudinal variation that we added by sampling repeatedly. That's where this is going. But to start with, for cross-sectional data, just to get the vocabulary right, let's say that I wanted to predict this person's outcome. Well, for this person, the mean is not a very good guess. So the mean in this flipped over histogram here is 90. This person is off from that by minus 58. They're much lower than the mean. So this one value for beta 0 here for my fixed intercept, this is the model for the means. And I think that's where the term comes from, is because as we add predictors to the model, it's still a mean in the sense that anybody who has the same values of those predictors would get the same expected outcome. It just becomes a conditional mean, meaning this is the mean for somebody who has an x of 5 and a z of 12. It's conditional, but it's still a mean. So in this case, the best guess for everybody is just this 90. So the variability that is left over is just the definition of variance. If you deviate each person's outcome from the grand mean, that is how you calculate variance. So even though, like on your software, this number might be labeled as residual variance, it's all the variance because nothing has explained it yet. In general linear modeling software, where would you find this on your output? Residual variance. Otherwise known as what? Do a little bit of review here. Where would you find the number that means residual variance on your output in a regression analysis? This is not a trick question, I swear. It's literally the first question for every single model that you would have done in homework with me with those two classes, and I guarantee you would have had it in anybody else's class as well. Starts with an M, then an S, mean squared error, mean square error, mean square residual. Yeah, that's where this shows up. In the software that we're going to use, there are no sums of squares because we're not using ordinarily squares. So you will get a line in your output that says basically residual variance instead, but it means the same thing conceptually. The way that we get to it is different. So let's say that we extend this example to 5 occasions for 3 different people. So we have to switch our notation first off. Y sub I becomes Y sub Ti, and apologies for the misuse of I across classes, but it can't be helped. I in this class is for individual person. T is for time, for occasion. So we'll have, in this case, 5 YTIs for each of my people here. So the fact that we have longitudinal data doesn't change the same logic as before. If you don't know anything else about a person, in an empty model with no predictors, what's your best guess for what their YTI is going to be? Say it again. The grand mean, still, yes. And now we have to make sure that we put the adjective fixed in front of it because there's going to be more than one kind of intercept. Fixed means everybody gets the same. The grand mean is the grand mean for everybody, so it's one number. But in longitudinal data, even though we don't have predictors per se, the fact that we know from which person each occasion came is going to help us make a better naive prediction than just the grand mean for everybody. Yes?
In this case, the fixed intercept of this grand mean is for both occasions and persons?
Yes.
Okay.
Yep. If all you have is a fixed intercept, then it is literally pooling just that entire column of y's and coming up with one number. If you have the second part that I'm about to introduce, then the fixed intercept becomes the mean of the person means, which, since I just gave it away, if I know from which person each data point came, I can say, well, why don't we give each person their own mean? Why don't we start with that? Wouldn't that be a better guess? Certainly. So this idea that we can use the repeated observations to come up with a better naive starting point, that increment is going to form what is going to be called the random intercept. Random means everybody gets their own. Random means that the intercept becomes a variable, not a constant. So the fixed part is the center of the variable. The random part is going to be the deviation for each person relative to that fixed center. So then, by giving each person their own mean, what we have effectively done is carve up the variability in that single column y into two sources. One is, why do people have different means? Well, I don't know, but they do, clearly. So we have between person differences in those person means, and this will eventually become level 2, but I'm sort of layering these ideas one at a time. Inter-individual differences. This is the part of the data that would have been there to start with. It's just that when you give each person a chance to answer more than once, the mean across their observations is probably a more reliable estimate of where they are on this variable than just any one shot. Think of it this way. If you had to pass a licensure exam to do your profession, like in nursing or counseling or law or anything else, would you rather have one question or 5 questions? 5, definitely. I'd like to have 100, please, right? Like more is better. So everything you learned about more is better in terms of reliability is still true. The mean that you get out of longitudinal data for each person should be a better estimate of their general tendency than any one observation can provide. But conceptually, the variability that exists cross-sectionally at one time is the same idea as this variability among the person means. It's between person differences. The extra part that we don't get in a cross-sectional study that we do get in a longitudinal study is the addition of within-person information. And that's why I have this plus WP up here, because the idea is that between person was already there, it's always going to already be there. We're adding the within-person part by sampling repeatedly. So then we can deviate each person's outcome relative to their own person mean, and then ask the question, okay, why are you off your mean today? Well, I don't know, but something. Those are within-person, longitudinal, intra-individual differences then. So this partitioning, and I'm deliberately using these words like partition or decompose or separate, we're not explaining variance. We are figuring out what kind of variance we have to explain. How much of what we thought was a longitudinal outcome is actually just between person versus actually longitudinal. So let's say that we have hypothetical data. Let's say that the black line is the average across time, and then here's a bunch of individual people. So this might be an example of a longitudinal study where time is somewhat irrelevant, or it's a construct that isn't expected to change. You just happen to have 5 measures of it. In thinking about what error means, if I were to fit just a standard general linear model regression to these longitudinal data, because each person has 5 occasions, they'd have 5 E's. So this is my hypothetical purple person here. Their E would cover all of the distance between the grand mean that everybody shares and their individual data point at each occasion. So each of these E's has something in common. It's going to be negative because the purple person is below the grand mean all the time. That means the E's are going to be related to each other, which is not supposed to be the case in regression. So we're going to fix it. We're going to introduce a new intermediate baseline on the basis of each person's person mean. And then we're going to say, no, wait a minute. This purple person's below average all the time. Let's give them their own mean. And then let's keep track of the distance between the grand mean for everybody and their own mean, and that distance, that difference, that deviation has a name. It's a random intercept. U is our new letter. Welcome to the model for the variance U. It's U0 because it's an intercept, goes with beta 0. It's an I because everybody gets their own. Each person has one U0 term that their entire set of outcomes shares, because U0 is how far off their person mean is from the grand mean. From there, E steps in to fill what is left. How far off are you right now relative to the person mean that is expected for you? And if this model fits, then these E's are supposed to be independent, they're supposed to have constant variance, and they're supposed to be normally distributed. The latter we can fix by switching to a generalized model as needed. Constant variance, though, the only way that that can happen is if everybody has mostly parallel lines. If people grow at different rates, then constant variance can't work. But we're starting with sort of parallel as a baseline for now. Okay, how are we doing so far? Good? Nods, thumbs, zoomers, we're good? Now that you can see what I'm looking at? Good. So what we have done, you can think of it several different ways. We've cut up the variance in Y into two different kinds. We have also, from a stats point of view, introduced this random intercept U0I term to handle dependency. U0 is supposed to be the reason the E's used to be correlated. After controlling for U0, the E's aren't supposed to be correlated anymore. Then you're back to your regular linear model assumptions about E's being unrelated to each other. So this random intercept is supposed to be the reason why they were related. Because people start out differently, some people are higher or lower, the end. That is the reason for the dependency. So then putting that back on our picture, each person has one U0 intercept that holds throughout their data. And just like we don't typically pay attention to the individual E values in regression, we don't pay attention to the individual U0 values. In fact, you will never see them unless you ask for them to be predicted specifically. They're an idea. Instead, what we're going to see is their variability across people. And the notation that I'm using for this is pretty standard in terms of multi-level texts. Tau squared, and then the subscript tells you what it is the variance of. So I read this as the variance of the random intercept specifically, given the way that I've written it. So this is a between-person variance. It represents all of the set of deviations of each person's mean relative to the grand mean. Why do some people have higher means than others? I don't know, but we can find out. So this is level 2 random intercept variance. After we control for each person's tendency to be higher or lower over time, then ETI is the residual at each occasion. And so then we're going to call this level 1. I will always use these terms consistently to avoid confusion. It's level 1 residuals and level 2 random intercepts. So just like it is in regression terminology, the variance across occasions, T, and people, I, is one number, sigma squared E. So that looks like residual variance that you're probably used to, but it means something different. It's level 1 variance, which means over time, not over people. So this is intra-individual variation. If you're like, yeah, I don't like pictures, can you show me a model? Sure, I can. So we are contrasting two different models for the variance on this slide. What they share in common is that they both are what we would call an empty means or unconditional model. Beta 0 is the only thing that's common across people in contributing to a score. So at the top, Y sub I matches E sub I. This model would be appropriate for one occasion. The lower model would be probably the simplest model you would entertain for longitudinal data. So they're both like the simplest baseline that you would have for that type of design. So beta 0 does not yet have a subscript, doesn't have an I, because beta 0 is a constant. It is a fixed intercept that everyone shares. The U0 part is the extra that adds to the mean, the grand mean to get to the person's mean. So if I'm somebody who's higher than average, my U0 is positive. If I'm somebody who's lower than average, my U0 is negative. So you can't interpret what the absolute amount is until you have both of these two things together. Beta 0 is the middle. U0 is how far off you are from that middle. And then E is what's left. All right. Yeah, I think I want to do that next. Questions or comments? Yes, please. This one or one more?
Yes.
Sure.
So after you introduce this new mean, initially they were all negatives, the errors were all negatives. So what happened here? How am I going to interpret this?
Can you say the middle part again? I couldn't quite hear you.
Initially you realized that all the errors are below, and then you said they were all negative.
Yes.
And after you introduce this new one, how are you going to interpret it? Do we say that we have a negative, positive, negative, positive?
Yes, you do. Yes. So let me repeat the question in case the Zoomers or the audio couldn't hear. She's asking, like, how do I think about what E means on this slide versus that slide? Is that basically it? Okay, good. So in this case, what E means is all of the deviation from what the model for the means predict to what you actually got that day. So in this case, E is negative because all of these points are below this black line. On the next slide, we have changed what E means. What used to be sort of total E has been broken into two pieces, where the new E is just this little deviation relative to the dotted line to each point. E has changed definition. So in this case, yeah, this E is negative relative to the dashed line. This E is positive relative to the dashed line. This one's negative again. This one's right on it, so it'd be 0, and so forth. So yeah, E means something different, because now E is just the within person deviations around a person's mean. Where that mean came from is being tracked by this U0 random intercept instead. But if you add them back together, it won't work exactly, but it will be very, very close in balanced data at least. U0 plus E, like that will get you back to your total variation that would have been there in this previous model. It's literally just cutting them up into pieces. Okay, did that help?
Thank you.
Sure. Other questions? Yes.
I have two comments. Can you go back to the equation or model slide?
This one?
Yes.
Okay.
So in this case, in the empty means part, can I assume that when we add the random intercept part, we are not changing the estimation of the conditional means?
Are you asking if beta 0 would be the same here and here?
Exactly.
Okay, depends. It will be very close, but it may not be exactly depending on whether you have balanced data. So in particular, if each person contributes a different number of occasions, then these two beta zeros will not be exactly the same number. The first beta 0 will be literally, like if you just take the entire column of data, everyone's y's across all the occasions and all the people and make a mean out of that, that's beta 0. The second one is the mean of the person means. Now, if everybody has the same set of observations, those will be the same thing. But if each person contributes a different number of observations, then beta 0 will not be the same across, but it will be close. The interpretation is different. But common part that everybody shares is a label you can keep in your head regardless. Okay. Other questions or comments? You had a second one. Go for it.
Yes. So there I have the random intercept, but I'm not including the random intercept in the model for the means.
That's correct.
And here I'm interested in the tau square U, which is the covariance across the inter-individual differences in random intercepts.
The tau, so the variance of these U's
Yes.
across people is going to create the covariance across time.
Okay.
Yeah, I think you're getting like 3 slides ahead maybe, but yes, you're headed in the right direction.
Okay, great.
But yeah, in the same way that like in regression, we don't ever see these E's on the output. Like you could ask for them to be saved to a data set, but there's really not much point. Like we just want to know how much of this E variance we had before and how much do we have now and what was our R square for that difference. It's going to be the same here. You don't actually ever get these U zeros because they're random effects. For those of you in the next class, they're factor scores. I know. You don't ever need the factor scores. You can just work with the circles, directly speaking. And we care about this U variance, how much was there to begin with, how much is still there after we add person-level predictors. Likewise, we care about how much of the variance is due to E, and then how much of it is still there after we add time-varying predictors such as time. So this sets up the stage for why R squared gets real complicated real fast. How many R squares were there in multiple regression in a given model? Like 1, right? This is the variance that it was, this is what it is now. You might be able to say, well, how much did it change relative to some other model? But there's only one number to keep track of in terms of what variance is. Guess how many we have here? 2. And this is just week 2 of this class, right? By the end of the semester, we'll have like 4 of these things. And so each one represents a distinct kind of variability to be explained by distinct kinds of predictors. But basically, anything that's a U, that's a random effect, so random intercepts and random slopes are special cases of the term effect. The only way to explain this is person-level information. Why are some people higher or lower than other people has to be explained by a characteristic of a person that does not change. E then is, why are you off your mean today? Why are you lower now than you were usually? Well, it has to be something that happened today. It has to be a time-specific predictor that would explain why those E's are the way that they are around the line. Okay, good? Good. Question? Yes?
So the end goal is to do this so that the E is randomly, it's a random, it's random error, it's not caused by...
There's no more dependency.
Okay.
Yes, yes. Yeah, if you do this correctly, the E that you end up with is just like it was in regression. Independent, constant variance, and normal, but that part is you can fix that for different kinds of outcomes. But yeah, that's one way to think about it is like, what are all the reasons why the E's were related and how do you build those into your model? Yep. And those reasons then imply opportunities for prediction. Okay, so then, very first thing that you would put in your methods section in a longitudinal analysis, interclass correlation from this empty means random intercept model. There's a lot of different terms for what this model might be called. I like empty means because that's the most transparent. You might also hear unconditional model or unconditional means model or random intercept only model, but the random intercept part is that has nothing to do with what's on this side. The key idea is that there's no predictors yet. Empty. So we use this model to compute a proportion that describes how much of our longitudinal data is actually cross-sectional. So I have this explained as many ways as I can think of. This is our friend intraclass correlation. It's ICC1 in HLM notation. And if you're thinking, wait, is that interclass correlation like I learned about in some other context? Yes, it is. More general, interclass correlation is a ratio of variances, and there's a whole bunch of different ones that are used for different purposes. This one is, the denominator is the total. So if I have the between-person variance in my random intercepts plus the within-person variance in my level 1 residuals. So the notation that we introduced is at the end of the chain. The words that it represents is in the middle here. And I can do that because all of these models say that the U's and the E's are uncorrelated. That is by definition. You cannot fix that. It would just break the whole thing. So level-specific terms have nothing to do with each other in terms of the model for the variance. So that's my denominator, is total variance. Over time, over persons. Again, thinking of this as one column of data that's going to be analyzed. All of the observations over time have been stacked into one column. The numerator then is the random intercept between person level 2 mean differences part. So you can think of this ratio in a couple different ways. The easiest way I think of is just to look at it as a proportion. Of the total variation, what proportion is due to level 2 between person random intercept mean differences? So that's the one that I prefer. That's one definition. The other has to do with the idea of interclass correlation as a correlation. This number is also the average correlation of occasions from the same person. Because what this model is predicting is an overall variance covariance matrix that looks like this. So in these matrices, you will see a whole bunch of these this semester. They are square matrices where it's per occasion across the rows. So like this term right here, row 1, column 1, is the variability in total at the first occasion. The next element on the diagonal is the variability at the second occasion, third occasion, and so forth. So you would have as many rows and columns as you have occasions. So on the diagonal, this term that creates total variance is the same thing as the denominator. The total variability across people at time 1 is this. The total variability across people at time 2 is this, and they're the same. This model predicts that the variability stays the same over time. The covariance, the thing in the off diagonal. So this is how related time 1 is to time 2 in the units that you're talking about. And if I standardize that covariance into a correlation, and here's the formula by which you would do that, then that correlation becomes the interclass correlation. So interclass correlation is how related on average occasions are from the same person. The way that this is constructed creates a range of 0 to 1. You cannot have a negative interclass correlation when constructed this way because variances can't be negative. So if it were a correlation, say, of 0.9, what that means is that 90% of the variation is because some people are higher or lower on average, and 10% has to do with which occasion it is, the E deviations around those person means. If you think of it from a prediction standpoint, do I have those slides in here? Did I get rid of them? Yeah, I think I got rid of them. I used to have slides about this, but I think they're gone. From a prediction standpoint, like if I know your score at time 1 and the interclass correlation is 0.9, I have a really good shot at guessing what your score is at time 2 or time 3 because they're all really related to each other. So the stronger the interclass correlation, the stronger the force is of the person in creating this variability. So an interclass correlation of 0.9 would be 90% of the action here is some people are higher or lower, period. 10% of the action has to do with what occasion it is. An interclass correlation, say, of 0.2 would be the opposite. Then it would be 20% is because of who's who, 80% is because of which occasion it is. Yes?
So that 80%, would you, I mean, I know you talked about like fluctuation and change in the past, but would that 80% be somewhat attributable to just like crazy differences, fluctuation across observations in an individual?
So the question was, if I have 80% of the variation that's over time, do I know if that's change or fluctuation or some mismatch of both? I do not yet know. It just means that they didn't give you the exact same answer every single time. Whether that 80% has something systematic in terms of change over time or whether it's just random fluctuation, we don't know that yet. Eventually, I will show you how to do a significance test for whether or not this interclass correlation is significant. And what it amounts to is comparing the fit of a model where everything is thought to be E against the fit of a model where we add this random intercept part. And if the model fits better, then we say we keep the random intercept and that there is some presence of between-person differences. Given that significance test, interclass correlation is the corresponding effect size. How much random intercept variance do we have? A significant amount. Great. How much is that? 20%. Okay, I can work with 20%. Couple things on this. You will see people use rules of thumb or provide guidelines as to what interclass correlation is ignorable. Pretend you never read that. The only interclass correlation that is ignorable is, what do you think?
0.
0. But not even then. Because what you will see, this is probably 3 weeks from now, but I'm going to foreshadow, because it's so exciting, I want you to come back and be on the edge of your seats. The way that these things get estimated, every time that E variance goes down, U variance has to go up in a compensatory fashion. They are yoked together in terms of their estimation. So that means that even if it looked like there was no U variance to start with, after you explain E variance, it will come back. So it may not stay 0. And there is a formula for what's known as a design effect that shows up much more often in other multi-level contexts because longitudinal people just assume that the person matters. The design effect is the sample size per person minus 1 times interclass correlation. So as long as you have an interclass correlation above to 0, you have a design effect. That then you divide your sample size by that, and that's the amount of actual information that you have. So to the extent that occasions are related, it's not like you have that much sample size. There's redundancy in there that you have to take into account. So the redundancy depends on the interclass correlation. If it's truly 0, let's say I have 100 people, 5 occasions each. If the interclass correlation is truly 0, then I have 500 observations, and they're all independent. If the interclass correlation is 1, how many observations do I really have? In terms of the information they provide. If the interclass correlation is 1, and I've got 5 occasions per person and 100 people.
100.
100. Yeah. An interclass correlation of 1 means they gave you the same answer all 5 times. You got 100 people's worth of information there. Somewhere between the two is what is most likely, right? And so that's one of the things, the very last chapter of my textbook goes into sample size planning for analyses and studies and things. Trying to anticipate what your power is at level 1, you have to be able to anticipate what your interclass correlation is to go with it, or at least a range thereof. Once upon a time, when I was a postdoc at Penn State, I used to have folks analyze their own data for their class, and their very first assignment was to calculate an interclass correlation on their data. I told this story in workshop this summer, so if you've heard it, pretend you haven't. It's a true story. And one of the people in the class came back and had an interclass correlation of 0.999999999. So after checking their code and their data to make sure that it was right, I asked to speak with him. And his whole reason for taking the class is that he was going to be the first in his area to do a longitudinal analysis of these data, and it was going to be new and exciting. And I had to break it to him and say, no, you're not. You don't have longitudinal data. An interclass correlation of 1 means they told you the same damn thing every time you asked them. And so, 1 second, I don't know what happened to this person because he dropped the class. But after feeling bad for like 5 minutes, I thought, no, I did him a favor. Because we were having this conversation in January and not mid-April at his dissertation defense when he didn't find anything. There is nothing to be found, is the answer. Interclass correlation of 1 means game over for longitudinal. Anything less than that, play ball. Question?
Would a contingency table kind of reveal that if people are answering the same way repeatedly?
If you're talking about categorical data, yeah, then you'd have everything's on the diagonal and nothing would be on the off diagonals for disagreement. You could think of it that way. Yep. So as long as there's at least some information that's within, we don't know if it's change or fluctuation yet, we just know that there's something to work with. Question in the back?
What if we're talking about like the 2 time points being correlated? What if you have more than 2 time points and the correlation varies between them?
Ah, not according to this model. Eh.
So if you have like a nonlinear change, essentially.
There are many reasons why these correlations would not be the same over time. Nonlinear change or even linear change is one of them. The fact that occasions closer together tend to be more related in almost every context is another, but not according to this model. So this is the simplest model that one would entertain for longitudinal data. It is rarely sufficient, though. That's one of the reasons. Another is what's on the diagonal here. Equal variance over time. The only way that can happen is parallel lines. Non-parallel lines, people change differently. They got to spread out. Variance has to change. So yeah, this model assumes, this model says, this is what the data look like. The data have equal variance on the diagonal. The data have equal covariances across all of the occasions regardless of how far apart they are. The covariance is caused by this random intercept in this idea. Probably wrong. This pattern, equal variance and equal covariance, has a special name. Does anyone know the special name?
Compound symmetry?
Yeah, compound symmetry. That's like a blast from the past in terms of my ANOVA language. Compound symmetry, this type of random intercept model, this is the basis of what we would call repeated measures ANOVA. The univariate approach specifically, which when I was in undergrad and grad school, that was the only kind I knew about. It wasn't until later that I knew there was another kind. I should have known that, though, in retrospect, because one of the things that I was taught to do in my repeated measures ANOVA is look for this like sphericity test box. Does this sound familiar? Like Wynn Felt and somebody, and somebody, a whole bunch of different people who made up the same shit in terms of sphericity tests. Sphericity is equal variance and covariance of pairwise differences over time. So it's slightly less restrictive than this, but it's basically the same idea. And I was taught, well, if those guys' tests are significant, you got to go look at this box instead. This box instead is multivariate repeated measures ANOVA, where it has a different pattern than this. And so that's one of the first things that I want to show you is what is the link between what we're going to do and what that is. The short answer is that because of least squares estimation, ANOVA only comes in two flavors. Everything's the same or everything's different. If you switch estimation, then you get a lot more choices. You can customize it to better match the data and not have to have complete data, which is a bonus. So, all right, are you waving at me or
Well,
just,
no,
okay.
I think you, so can you impute within the setup if you're missing data?
You can, but you don't have to.
Okay.
Question was, can you impute? So let me say that more generally. If you're talking single imputation, like you just fill in a hole, like with conditional regression or mean imputation, no. Super, super wrong, never ever. Multiple imputation, when you do that a whole bunch of times and you add an error term each time, that's okay, assuming your distributional assumptions are correct. But if you have the same predictors that build that imputation model as in your analysis, they are asymptotically equivalent. You don't need to. I have never actually done multiple imputation to address missing data in my life. I always try to find a way to hack it with maximum likelihood instead, or Bayes, as it were. Okay, that's a lot of words for one slide. Other questions? I like the questions, though. If I didn't want the questions, I would just record these videos in my basement and let you watch them at your leisure. I like your questions. All right, so then adding stuff, because nobody ever woke up in the morning and said, you know, I really feel like estimating an empty model today. That never, ever answered, you know, aim one of anyone's grant. So once we add predictors, they can be time invariant, they can be time varying, whatever. For right now, the purpose of this discussion is really focusing on the variance part. So after we add predictors, each of these variances is still there, but it should be reduced. Predictors that are constant to a person, predictors that are level 2 cross-sectional time invariant between person things, they're going to capture this U0 tau squared variance. Within person change over time level 1 micro longitudinal time varying things are going to capture this E variance. And so we'll watch each of them go down As the E variance goes down, the U variance is also going to go back up a little bit, though. So it makes it tricky. All right. We did make it to the example. How about that? So I made up some data to show you what happens in terms of testing predictors if you have that U0 variance in the model versus if you don't. So here are the results that we're going to get in this fictitious design. I've got 50 kids, and they're either in a treatment group or a control group, and they've each been measured twice. And so the idea here is that this would be a classic pre-test, post-test design, where I'm hoping that the kids in the treatment group grow more than the kids in the control group. And if you look at the means that are inside these squares, it kind of looks like that's what happened. The little numbers that are on the rows here, these are differences. So the difference between 49.08 and 54.9 is this 5.82. Likewise, the difference between these two cells right here is 1.68. These are right here. And the one in the middle is going to be the interaction term. An interaction term is a difference of a difference. So you can either think about this too as how the time effect differs between control and treatment. So how this difference going this way across differs from this difference going this way across in this row. Or you can think of it going down the columns, the difference between groups at pre-test relative to the difference between groups at post-test. How different are the group differences is the interaction term. Group differences and change over time is also the interaction term. So all of these numbers are going to stay exactly the same regardless of what my model for the variance is, because this is balanced complete data, and all of these terms related to effects of group, time, and their interaction are in the model for the means. What's going to change, though, are our inferences. The standard errors for these things will change in some spots, which causes the p-values to change. So that's the part that I want to walk through with you, as well as to introduce you to the code that we will use to estimate longitudinal models in our 3 packages of choice. All right, you ready to see it? Why not, right? We're all here. And I didn't even open it because I didn't think we'd get there, and I should have. Of course, now this thing is mad at me. That's never a good sign when you have like the hourglass of death. Can I please have my document or no? What if I shut off Dropbox? Then can I have it? Let's find out. Yes, go ahead and check your email or whatever. Text your friends. I can't believe Lisa's computer is freezing in the middle of her lecture. It happens. Hang on. Yeah, it's really mad. No? I don't get to have example 3A? What if I ask nicely? What if I open it as a PDF? Ooh, that looks promising. Maybe. The laptop that I used to have at KU would decide to update itself randomly. You didn't have control over it. It was an admin thing. And it actually update and shut itself off during my class one time.
They used to do that here too, and then they changed it eventually for that reason.
All right, hang on here, friends. My whole thing is locked up. I'm going to hit